All right, so let's practice a couple more times with De Moivre's theorem. I have to like pause before I say it, otherwise I mess it up. All right, so I've got 1 minus I to the 9th, so I'm in rectangular coordinates, and it's going to be a whole lot easier if I translate into exponential first. So if I plot this, I've got a 1 and a negative 1, so we already know that this is going to be root 2, okay, because it's a right isosceles triangle. So where, if my radius is root 2, where does my, where does sine or cosine have a ratio of root 2 over 2 in quadrant 4? Okay, so that's going to be a theta of 7 pi over 4. So now I can convert to exponential and then raise it to the 9th power. So my radius is going to be root 2 e to the I 7 pi over 4, and now raise that to the 9th. So remember that root 2 can be rewritten as root 2 times root 2 to the 8th. Okay, so I kind of sort of messed up how I just said that. Root 2 to the 9th can be root 2 times root 2 to the 8th. Okay, because you would same base, add your exponents, which means what I've got is a root 2, and then this is a 2 to the 1/2 to the 8th power. So that becomes 2 to the 4th. So 2 to the 4th is going to be 16 root 2. So my radius becomes 16 root 2 e to the, and now I have I to the 63 pi's over 4. So I want this to be within 1 lap of the unit circles. So I'm going to subtract off multiples of 8 pi over 4. So a close multiple of 8 pi over 4 is going to be 56 pi over 4. So 63 pi's over 4 minus 63 pi's over 4 minus 56 pi's over 4, which is 7 laps at 8 pi's over 4, will give me 7 pi's over 4. So I now have 16 root 2 e to the I 7 pi over 4. So that's exponential. And now go to polar. So 16 root 2 cosine 7 pi over 4 plus I sine 7 pi over 4. And now go to rectangular. So 16 root 2. The cosine of 7 pi over 4 is root 2 over 2. Plus I times the sine of 7 pi over 4 is negative root 2 over 2. So 16 divided by 2 is 8. Root 2 times itself is 2. So basically it's 16. Okay. So this reduced, all right, so 16 times root 2 is going to be 16 times 2, which is 32. And then divide that by 2, which is 16. So I end up with a 16 minus 16i. 16 minus 16i. So finally, for the last one, what we will do is, actually, you can do the last one. Actually, we'll just do it. All right, so I've got root 14 minus I. I'm going to take that to the 4th. So this is root 14. This is minus 1 I. Okay, so Pythagorean theorem says this side squared plus this side squared is r squared. So I get root 15 is r. Okay, so root 14 times itself is 14. Negative 1 times itself is 1. So 14 plus 1 is 15. Take the square root of both sides, you get root 15. So I know that now this angle is not a benchmark angle. Okay, this angle is not a benchmark angle. So we're going to go ahead and set this thing up as the radius, which is root 15, times e to the I. And then since I'm in quadrant 4, and I'm going to have to find an angle using ratios, okay? I'm in quadrant 4, which means I'm going to choose to use arcsine, okay? So I will have the arcsine of negative 1 over root 15. I'm not going to use arc cosine because I'm not in quadrants 1 and 2. So I'll have the arc sine of -1 over root 15. And I can get a decimal approximation for that. And then I can go ahead and convert. So my theta will be a decimal approximation. Okay, so going back into, oops, sorry, hang on, raise that to the 4th. So root 15 raised to the 4th power is going to be 225. And I'll have e raised to the I times 4 arc sine of -1 over root 15. Okay, and for sake of time, I'm going to let you finish that out. So, because it's just calculator stuff. So you'll have the cosine of the arc sine times 4. Okay, so 4 times the cosine of the arc sine of -1 root 15 plus I times the sine of the arc sine of -1 root 15. And then find those decimal approximations. Okay, and I forgot the 4. Here's a 4. All right, so find those decimal approximations, and then you can convert into rectangular. So what we want to do for the last couple is we want to find roots. So this is going to be the last thing that I typed up for you on your notes. And there was a typo. I fixed it. I forgot the I. So I want to find complex roots. So if I'm going to find the complex cube roots, there are exactly 3 of them. If I'm going to find the complex 17th roots, there are exactly 17 of them. Okay. So what I notice first is I'm going to do the complex cube roots of 13 plus 13i. So that's rectangular. So when I notice for the application of this, I notice that I want this in exponential. So I'm going to go ahead and find exponential. So I'm in quadrant 1. This is going to be over 13, up 13. So it's a right triangle. So this must be 13 root 2. Okay. And then what I want to do is go ahead and find the exponential notation. So first of all, we also know that you're in pi over 4. Okay, your theta is pi over 4. So my radius is 13 root 2, and my theta is going to be a pi over 4. So one of the things that I should probably add to this is that if I'm finding 3 roots, so I'm going to find the 3rd root, okay, which is what I'm actually doing. I'm doing a cubed root. Okay, so it's defined to use the cubed root. I'm going to use k equals 0, 1, and 2. Okay, and you're like, what is she talking about? Hang on just a second. Just recognize that you need to start your iterations at 0 and not at 1. Okay, so again, what is she saying? I want the complex cubed roots of z. Okay, so if I have this, that means I'm going to take the nth root of my radius. So I have the nth root of my radius. So what root am I taking? I'm taking a 3rd root of my radius. Okay. And then I've got e to the, so e to the, and then you'll notice that I forgot my I, but you've got a 1 over, what root are we taking? A cubed root. So this is going to be 1/3 I. And then I've got my theta plus multiples of 2 pi. So my theta is pi over 4 plus 2 pi k. So I'm going to do this 3 times because I'm finding 3 complex cubed roots. Okay, so I've already got this part set up. I've already got this part set up. All I've got to do is figure what this is 3 times. And this is where k comes in. The first time you're going to use a 0. So 2 pi times 0 is just going to give you pi over 4. Then I'm going to use a 1. So I'm going to have 2 pi times 1. So I'm going to have to add 8 pi's over 4 to pi over 4 and then simplify. And then I'm going to use a 2. Okay. So my first root is going to be z sub 0 is going to be a cubed root of 13 root 2. E to the, And now I'm going to come over here and do this. I've got pi over 4 plus 2 pi times 0. So pi over 4 plus 2 pi times 0. See the 0? Okay. So that's just pi over 4. Well, pi over 4 times 1/3 is pi over 12. So I've got pi over 12 times I. So that's the first one. The second one, which is z sub 1, is going to be the cubed root of my radius. And then I have e to the, and now I need to know what my exponent is. So I've got pi over 4 plus 2 pi times 1. So I've got a 0, a 1, and I'm going to do a 2. So pi over 4 plus 2 pi's is pi over 4 times 8 pi's over 4, which is 9 pi's over 4. And 9 pi's over 4 times pi over, times 1/3, sorry. Just let me throw a pi in there. Okay, so 9 pi's over 4 times 1/3. Those are going to reduce, and I'm going to get 3 pi over 4. So I've got 3 pi over 4 times I. And then for my final one, my k is 2, so k is 0, 1, 2. I've got the cubed root of 13 root 2 e to the I, which I'll fix in a second. And I'm going to shove in a k value of 2. So if my k is 2, that means I've got pi over 4 plus 4 pi's. Okay, so that's 16 pi's, 17 pi's. So 16 pi's over 4 plus a pi over 4 is 17 pi's over 4 times 1/3 is 17 pi's over 12. So 17 pi's over 12 I. So those are your 3 complex cubed roots. Now what you find out is that if you've got a circle, because we're in polar world, remember, and then we extended into rectangular world, what you found out is that if your radius is 13 root 2, okay, so my radius is 13 root 2, you found the 3 angle measures that will actually divide this thing, which I'm kind of sort of guessing. It will divide this, and so you've got 3 equal sectors, okay? So those are the angle measures that will make that happen. Now, let's do another one, and then we'll be done. So we have, let's do the complex 5th root of negative I. So the complex 5th root of negative 1 I. So this one is actually easier because this is found on a quadrantal angle. So if I'm at negative 1 I, then I find out that my radius is 1, and then how did I get over here? I swung over pi units. So my theta is pi. Okay, so my k's are going to go from 0 to 4. So I've got Z0, Z1, Z2, Z3, Z4. And notice that your radius is 1. So I'm going to write it the first time, and then I'm not going to write it anymore. Okay, so I have a 5th root. That's going to be static. I've got a 5th root of my radius times e to the 1 over 5. And then I've got my theta plus 2 pi. So let me write this up here. What we're doing every time is the 5th root of 1, e to the 1/5, and then I'll have pi plus multiples of 2 pi. Okay, so what have we got? 1/5 times, if my k is 0, I get pi. So this is just pi over 5. Okay, forgot my I. All right, see, what did I tell you? All right, so the 5th root of 1 is 1, which means your radius is going to be 1 the whole way through. So actually I can just change this to pi over 5 I. So the second one means I'm going to shove in a 1 here. So 2 pi's times 1 is 2 pi's, plus a pi is 3 pi's. So I'll have 3 pi's over 5. So this is e to the 3 pi's over 5 on I. This one is going to be shoving a 2. So I've got 1 pi plus 4 pi's is 5 pi's over 5 is a pi. So I have e to the pi I. Okay? And then for the third one, I'm going to have 2 pi times 3 is 6 pi's, 7 pi's over 5. So e to the 7 pi's over 5i. And then for the fourth one, I'll have 2 pi times 4 is 8 pi's, 9 pi's over 5. So e to the 9 pi's over 5i. Okay, so again, you've got a fifth root of 1 in front of all of these, but that's just 1, so it's kind of pointless to write it. Okay, that is section 2, the end of this section.